Hello, everyone. This is probably going to be a little bit on the shorter side of recordings, but I wanted to talk a little bit, by far not all I can talk about, but a little bit about what does it mean to know that you have a stable converged simulation. So, first things first, I'm going to do my damnedest to try and mess up this simulation to show you what a unstable simulation looks like. Let me see how I can do this. We're going to do this by messing with boundary conditions, because this is probably one of the more reliable ways to mess with stability, is have physically implausibly defined boundary conditions. Actually, you know what? Screw it. 160 meters per second will probably crash this. Let's see here. Thinks it figured out something. Aha. There we go. So, two things. You see this plot called residuals. This will always be there. This is kind of important. And what this does is it plots a quantity that is sort of a leftover quantity. And I'll get to that in a second. But in general, you want these residuals to go down. If you see them ever start to go up, well, or at least steadily up in like a straight line like this on this graph, note that this is a logarithmic graph. If you see them start to go up like this, your simulation is probably going to crash. If it goes up like this for very long, at least. If you see an error that looks like this, a non-finite residual or other quantity was added by some insert string here. Typical causes are overflow, underflow, or division by zero. Well, this means that a number has gotten generally large enough where you can no longer represent it with a single or a double floating point number, depending. This means your simulation has crashed. It was horrendously unstable, and it crashed. Or just, it was unstable, and it crashed. This is bad. This error means your simulation is not stable, or a type of error that looks even vaguely like this means your simulation is not stable. What you like to see, I'm going to clear the simulation, and if this happens, you have to clear your solution. So solution, clear solution. I'm going to set this back to the way it was. I'm going to make that a pressure outlet again. And hit run. This simulation is stable, but it's really not all that brilliantly converged. Let's see here. So stable and convergence are two different things. We want both as best as we can get them. So stable basically means it doesn't blow up. You don't get that error. That is a stable simulation. You can have more stable or less stable simulations, but it is somewhat stable if it doesn't blow up, as we saw a moment ago. These residuals are kind of what we use to gauge a little bit how stable it is, but this isn't the end all be all. That's important to know. So the way it's solving this is basically there's I'm not a hardcore math guy. The math under the hood of this is way out of my league, to be fair. But it uses, to some extent, series expansions. And one of the nice things about series expansions is that you can't do the entire series expansion, right? They go on to infinity. But you can know mathematically, at least for certain types of series expansions, certainly, exactly how much error you're introducing by stopping that series expansion at some point. So at some point, the computer's like, okay, we've done enough calculations. how much do we have left over? Well, the amount that's left over, so to speak, is kind of conceptually how I view the residuals. I probably have, from a true math perspective, have this horrendously incorrect. Uh, but it's from a high level conceptual thing, it works to think of it that way. This is how much is left over on any of these equations that we're using. The residual from these equations. If you have a little bit left over, that's good. You're not leaving very much behind. When you stop that series expansion, you didn't introduce very much air, which is great. You don't want very much air. You want the smallest amount of air possible. And it's solving a whole bunch of different equations, right? It's solving turbulence equations, two turbulence equations in this case, SDR and TK, because this is K omega. It's solving an energy equation, an X momentum equation, a Y momentum equation, and a continuity equation. So as it solves these, it truncates that series expansion and has some amount left over. How much is left over? Well, the answer is that is a number, right? It is a defined number with dimension, with quantity. But that's not what we're looking at here. What we're looking at here by default is what is known as a normalized residual. It says, okay, whatever was left over off of that series expansion when I started the simulation at an iteration like, I think it does like an average value over iteration about 1 through 5, but how much was left over when I started the simulation? Okay, that is considered a value of 1. If I have less left over than when I started the simulation, that is a value less than 1. If I have more left over from truncating this series expansion, then that is a value of more than 1. Ideally, what you like to see is your values fall 3 orders of magnitude. You want all your residuals in an ideal world below 0.001. That means you're left with 0.1% of the truncation error that you started with. Now, that's a rule of thumb. It can be broken because, again, these are normalized. Hypothetically, if you started a simulation that was exactly the same as the way it as physical reality, well, guess what? You would still have a residual of 1 because it would start to simulate it and it would be like, yeah, this is right. I don't need to change anything. And it would just stay that way. Your residual would stay at 1 because it's normalized. Likewise, if you have an exceptionally complex flow field, there's a lot going on. Complex interdependent effects. Well, you might need to have your residuals fall more than 3 orders of magnitude to converge because it was just not very, it was very far away from reality when you started it. So 3 orders of magnitude worth of drop is a rule of thumb. And this is getting nowhere near that. I don't think we initialize. Let me double check here. I don't know if this was initialized to any value. So let's see here. Initial conditions. Oh, this is initialized. Absolutely. Okay. So your initial conditions can affect this greatly. But the rule of thumb is about 3 orders of magnitude. If it's a quantity you don't care as much about, maybe 2 is fine, but you want it to fall at least significantly for the most part. So this is stable, but not very well converged. If we look at a whole bunch of our plots here, look at our lift and drag plot, it's, I mean, it looks like it's a flat line, but it's oscillating a fair bit here. And part of the reason I say this isn't horribly accurate is because I know I messed up the mesh pretty badly, deliberately. I made it very coarse. So I'm going to make this mesh finer, and let's see how much this changes our residual curve. It's worth noting, when you change the mesh, you don't need to restart the simulation. I can start it from here, and it will interpolate and continue the simulation. Oh, it helps if I actually remesh it. I changed the mesh value, but I didn't actually tell it to run the mesh. So we'll let this finish meshing, and then we'll run it a little bit more and see what's what. But again, residuals are kind of a rule of thumb indicator. They don't tell you everything about it, because residuals aren't the quantity you care about. The quantity you care about is like maybe lift and drag and moment on a wing, right? Or maybe the quantity you care about is heat transfer through a surface, or mass flow rate through a nozzle, or any of a bazillion other things. Yeah. So you see, I ran it. Yeah, it's figuring it out. I remeshed it and I told it to run again, and all these values jumped up because suddenly it had to do a whole lot of interpolation, and that changed the flow field dramatically. And they're working on becoming stable again. Still not spectacular, but sort of better than it was. Except for this green one. This green one's kind of way up there. But notice how they're oscillating up and down a lot less. This is also a really bad sign. You don't want them oscillating vertically a whole lot. You want them to be as close to a flat line as you can get it. So I'm going to clear the solution really quickly here, and I'm actually going to set our initial conditions to 0 velocity and run it some more. The one of these that tends to be the highest pretty consistently is regularly the turbulent kinetic energy in most simulations that I've dealt with. Turbulent kinetic energy is regularly the most unstable quantity. Or rather, sorry, it's the quantity with the highest residual regularly. So you want to see a couple of things to know that a simulation is converged and to know how well it's converged. You want to be looking at this to see, are these, well, they're never really going to be flat lines, but are they kind of oscillating around a fixed value? And this is starting to get pretty close. This Y momentum is doing a little bit still, but this is pretty close to oscillating around fixed values. And notice that this is actually a lot higher than when it started. Again, this is a normalized residual. So what happened is, because this started with no velocity, there was no turbulence when the simulation started. As the flow started to move in, it got a significant amount of turbulence, and that is why the TKE is really high. The rest of these have dropped not quite. I mean, this one's dropped almost 3 orders of magnitude. This one's dropped almost 2. So it's not spectacular as far as convergence goes, but these are flatlined, right? They're no longer moving up or down. They're just oscillating irregularly, but oscillating around more or less fixed values. And the important thing we want to look at here is, what are the quantities that we care about? Have those stopped changing? So we can look at the leading edge, moment coefficient, the quarter chord moment coefficient. We can look at, let's see here, lift and drag. Have these stopped changing to an acceptable level? Well, the answer is these are mostly not changing, but they're still changing a little bit, it looks like. Zoom way in on this. So ideally, what we like to see is that these stop moving up or down and they just start oscillating around a fixed value. You can see this yellow line is oscillating a little bit. And it's still kind of climbing really, really, really slowly. is look at the y-axis scale. We're talking tenths of a Newton of change. Like this entire y-axis is only 1 Newton tall. A little bit more than that now, but this is probably a small enough oscillation that I'm willing to call this converged. Again, could be slightly better, but this is almost certainly good enough for most applications. But again, what are the quantities you care about, right? Some things will converge relatively quickly. Like this was mostly converged inside of about 1,700 iterations. We probably didn't need to run it out to 2,400. However, if you're looking at other quantities, they might take a lot longer to converge. Like maybe temperature is a big one, actually. If you're dealing with anything with temperature, it typically takes a lot longer to converge than pressure-based phenomena. So it depends what you're looking for, how long you need to wait for convergence. Maybe you only need to wait for a basic something, like maybe it's only a couple hundred iterations and it'll know what's going on. That's possible. Or maybe it'll take tens of thousands of iterations. It depends what you're looking at. But the big thing is you're looking for where your quantities have stopped changing, and you're kind of assessing a little bit about where these residuals are relative to where they started. However, because these residuals are normalized, you have to take these with a big grain of salt because you have to know where they started. Now, if we want to debug a simulation and make it a little bit better, and this is going to be mostly it for this recording is after we talk about this part, we want to know where are these residuals coming from? Like where is it leaving the most behind when it computes these residuals in that series expansion? Because in some points in space, it's leaving basically nothing behind. In other points, it's leaving a lot behind. And this number is basically how much is it leaving together or leaving off of that series expansion everywhere in the simulation. So if we want to look at where it's leaving or where these residuals are coming from the most, we need to do a couple things. This is a little bit of a more advanced step, but can be invaluable for troubleshooting if you don't have an idea of where the problem is. Sometimes you'll have an idea of where. So what you can do here is go into the solver folder. In general, this is an advanced thing. I don't necessarily recommend dealing with this all the time, but you go into the solver folder and you can click on segregated flow. Actually, we'll click on pretty much all of these. We'll click on all 3 of these, and they all have a property called temporary storage retained. What this does is, if you check this, it will keep values that would otherwise throw out. Normally, when it computes residuals, it checks the residual of every cell. It adds them all together, and it gets a total residual value. And then it says, okay, I don't need the residual in these individual cells anymore. It takes the individual values and throws them out. It doesn't need them. They're gone. What temporary storage retained does is it retains those values. So it will keep those values around so you can look at them and see where the residuals are highest, which is important. If you need to know where your problems are coming from, it's probably where your residuals are high. So we can hit temporary storage retained, and we can run one more iteration because it already threw out the values from the last iteration. So we need to run one more so it computes those values and then keeps them. And then we can plot these values. Let's look at, these are values that are called residuals. So let's just type in residual to look for them. Perfect. Let's look at the X momentum residual. It looks like most of our residuals are probably coming from up here from the looks of it. Like, most of this is absurdly stable. This, not so much. Like, there's residuals up here. So, this is probably where our problem's coming from. Which is, we probably could have guessed that, honestly. Because if we look at a vector field of velocity, let's see here, we can see that it's got this kind of bleed through because the flow is being deflected downwards. But this is a pressure outlet. So let's see if we can change our boundary conditions a little bit to make this somewhat better. Maybe this will help. So if we look at our top boundary, it doesn't really want to be a pressure outlet. Let's turn it into a stagnation inlet and see what happens. Where's our residual plot? Well, it definitely changed things. It helped our turbulent kinetic energy a whole lot. It didn't particularly help anything else, though. Okay, let's mess around with this a little bit more. And let's say that this is a symmetry plane, let's say. Actually, let's check our residuals really fast. Actually, tell you what, we're going to put our residuals up on the side here. Oh, yeah, our problem is still basically up here. Apologies for the strobe effect. Let's go ahead and make this a symmetry plane. And switch back over here so we no longer have a strobing effect going on. That seems to... I mean, it's helping the residuals quite a bit in general. TKE isn't the most happy with us, but the rest of it is much happier than it was before. Right, they're getting down there in that 10 to the negative 3 neighborhood. The problem is the symmetry plane doesn't allow flow to move through it. Let's see here, velocity inlet. Boundary normal is very not what we want. Let's see here, though. And velocity inlet's probably not what we want. Let's just try a regular old outlet and see if that helps. So we can see that pretty much where all this turbulent kinetic energy part was coming from was the upper and lower surface here. Back. Let's switch this to an outlet. Oh, well, it didn't like that. See, that's what a crash looks like. it's pretty unhappy with this. But you can mess around with a couple of different settings. I'm going to put this back to a pressure outlet. And the bottom can also stay as a pressure outlet. Oh. You can mess around with boundary conditions to some extent, and more importantly, you can look at where are your residuals the highest. If you turn on temporary storage retained, you can plot where do you have the highest residuals. See where they are, see where they're going, and think about, okay, if this is the problem, or this is where the problem is, what can I do to fix this? Sometimes it's obvious, sometimes it's not. And sometimes you just have to experiment and think about it and basically be like, how do I get this to be the most accurate thing reasonably possible given the circumstances? Is it going to be perfectly accurate? Pretty much never. You're never going to get that. But is it accurate enough for what you're doing? That's the question. And sometimes it might be worth building a simplified model because it takes too long to fix the thing you're trying to fix. So you need to spend some time figuring out, okay, how do I fix this effectively? You might need to build a simpler model so you can fix it effectively. There are many things you might need to do to try and fix a thing in a time efficient manner. But checking the residuals and where they are is usually one of the more effective things to figure out, okay, how do I make this thing more stable, more accurate, make it converge better? So, just to kind of step out from the high level, if it's giving you that error, that is an unstable simulation and it is crashing. It is crashing because of residuals generally in some location. You can check the residuals by turning on temporary storage retained and looking at a scalar scene. Where are the residuals high? Where are they low? Okay. And then as far as how well converged it is, you want to, well, A, watch for when these values become flat lines. Not perfectly flat, but they'll oscillate around fixed values. You want to look for when your properties of interest stop changing. When your lift stops changing, when your drag stops changing. Like right now, these are both changing appreciably. Lift more so than drag, but they're both changing noticeably. Like we've already had like a full Newton change in drag pretty much. It might be oscillating right now, but lift is definitely changing noticeably right now. So you need to wait until the quantities of interest have stopped changing significantly. That's a converged simulation. Ideally, you want to see them oscillate perfectly around a fixed value, but sometimes that can take an unrealistically long time. But you need to make sure that, given a very long time to run, that there's not going to change enough where you're going to worry about how much the value changes. So that's the crash course in sort of getting an idea. Again, these are rules of thumb, not end all be all, but an idea of how converged and how stable your simulation is. It's really obvious when it's not stable because it'll crash. It's more difficult to determine how stable it is. Like, it's stable, yes, but how stable is it? How well converged is it? That's a little bit harder.